Hello, Mr. Claudia here. And finally, we are at the home stretch of the trig chapter. Now that we're comfortable with graphing trig functions, solving trig equations, the next step would be to look at the derivative of trig functions. Now again, we're very late in the course. I'm not going to go through a long proof of this. You could find the proof using first principles for these three derivative rules. You could also kind of think about it graphically. You know, the graph of sine reaches a maximum at 90 degrees, so that corresponds to a derivative of 0. So you could kind of go through it graphically. Either way, the derivative of sine is cos. The derivative of cos, negative sine. The derivative of tan is something else. It's cos. It's 1 over cos squared x, or secant squared x. This is not in IB, but I just like to have it there just for completedness. It's not in IB Math SL. Okay, but we have it there. Okay, so let's try using these. I mean, really, that's not the hardest derivative, right? Derivative of sine is cos, derivative of cos is negative sine. Let's try using it. This is hopefully going to bring back some memories about the derivative. To find the derivative of sine x, well, that's, okay, so, I mean, we're just told it. What's the derivative of sine something? It's cos something. So the derivative of sine 3x is just going to be cos 3x. But then I have to remember, well, what's the derivative of my interior function? So there is a chain rule requirement here. You didn't think it was going to be that easy. So then the derivative of 3x is just 3, so I end up with 3 cos 3x. Be careful, that 3 I can't just multiply with the 3 here. Those are kind of separate. So that is a situation where I had to use chain rule. And you can see anytime I have something inside the argument of the trig function, I'm going to have to use chain rule. Similarly, this next example, what's the derivative here? Well, dy dx, the derivative of cos is negative sine. So what's the derivative of cos something? It's going to be negative sine of that something. And then I have the derivative of the something, which is just 1. So it's just negative sine x plus 2. So there's the chain rule again. I didn't show as much work because you guys know chain rule, and as you do more of these and as it comes back, you won't you'll be able to jump right to this. You won't have to necessarily write the step if you don't want to. This next question, f of x is equal to sine x cubed. Be careful, because the x cubed, that means it's inside the bracket if I write it like that. So if I want to find the derivative of this, well, what's the derivative of sine something? The derivative of sine something is cos of that something times the derivative of the interior function. That's a confusing one. Let me write this out again. The derivative of x cubed. And that gives me 3x squared cos x cubed. That's a chain. Usually when I'm writing out trig functions with other variables and coefficients, write all the variables and coefficients first. It's a little bit more organized. Then you don't, it's like with ln and log, same issue. You won't accidentally mix up the argument of the trig, like the x cubed, with the 3x squared. So that's a good form. Okay, next question. I have sine squared 5x. What does sine squared mean here? I mean, this is something we get used to writing, but what it really means is sine 5x and then that whole thing squared. So be careful, and actually I'd recommend writing the question out like that. It'll make sure you don't make any kind of foolish error with this question. So now if I ask you for the derivative of sine, I actually have a function of something squared. What's the derivative of something squared? Well, the derivative here is 2 times that something to the power of 1 times the derivative of the interior function, which is sine 5x. So there's a chain. But actually, I'm not done. So what's the derivative of sine 5x? Well, look at what's happening here. I have 2 sine 5x now. And what's the derivative of sine something? Well, it's cos something. Then I also need to take the derivative of the interior function again, which this time is 5x. So it's actually a chain within a chain. So I end up with 2 sine 5x cos 5x, and then I have this 5 here, which gives me 10 sine 5x cos 5x. And I don't know if you see this. This is pretty neat though. Sine 5x cos 5x times 10. This is actually a double angle formula. This is going to be 5 sine 10x. It's a double angle. Remember my double angle identity. Sine 2 theta is equal to 2 times sine theta cos theta. So multiply this by 2 and then half the angles. So that might be a tough one to see. But if you had your formula sheet, you could see that. Where is it? Trig. There it is right there. So I had, instead of 2, I had 10. And then instead of theta, I had 5x. So now I'm going to double the angle, so I'm going to get 10x. And I'm going to double this, so I'm going to get, or half this, so I'm going to get 5. Anyways, that's a little obscure. We're more interested in the derivative. But it's kind of a neat thing. If you know, it's kind of cool. Okay, this question. What's the derivative of 1 over tan x? What's neat about this is that, well, there's a few ways of doing it. This is also known as cotangent x. That's one of those reciprocal functions. I know this isn't really in the course, but what's cool is that you can actually figure out all sorts of interesting trig ratios by using your trig identities. We know tan is equal to sine over cos. So this is 1 over sine over cos, which is really just cos over sine. Now, if you want to find the derivative of that, you can use your quotient rule. So the derivative of the top of cos is negative sine x times the bottom, which is sine x, minus the top, which is cos x, times the derivative of the bottom, which is positive cos x, over sine squared x, right, because I've squared it. And now I end up with negative sine squared x minus cos squared x over sine squared x. This is going to be, if I factor in a negative, I end up with sine squared x plus cos squared x over sine squared x. And if I replace this using my Pythagorean identity with 1, I get negative 1 over sine squared x, which is pretty neat. So you can look up in a book, what's the derivative of cotangent x? It's negative 1 over sine squared x. You guys could actually find that out. Or another way of writing this, it's negative cosecant squared x, technically. So it's kind of neat that you can use all the tools that we've learned and you can actually solve a lot of really complex derivatives. Okay, let's keep going. We have f is a product rule. I have a function times a function. So I'm going to have to use my product rule. So derivative of the first function, which is e to the x, times the second function, plus the first function times the derivative of the second function, which is cos. Can't do much more there. I mean, I could factor out the e to the x. But basically I'm done. Okay, and let's do this last question. I have s is equal to ln of sine. Well, what's the derivative of ln something? It would be 1 over that something. But then I have to remember chain rule and take the derivative of the something. The derivative of sine is cos, so I end up with cos t divided by sine t. This would be my chain rule. I should have said this is quotient rule. And this one over here was product rule. And what poor space management we have here. If I have cos over tan, that essentially is 1 over tan, or cotangent. So it's a pretty easy derivative, like to remember. It's on your formula sheet. The challenge is going to be, applying the correct chain rule, product rule, quotient rule, because it's very rare you're just going to be asked what's the derivative of sine. Okay, so that's the lesson. Now we're going to revisit all of the things we've learned to do with the derivative over our time in IB Math. So one of the first things we did, this was back in your grade 11 course, we had to find the equation of the tangent line. So this is something you could get. Maybe you haven't done one of these in a while. Here's a great opportunity to review. Remember, the equation of a tangent line should have the form y equals mx plus b. So the problem is I need to know what the slope is and the y-intercept. I don't know either of those, but I can figure out the slope of the tangent line by taking the derivative. So that'll be my first step. Anytime you see something like this, a question like this, and you're not sure what to do, a good plan is to just start by taking the derivative. So the derivative, or the slope of my tangent line, is equal to my derivative, dy dx. So let's find the derivative of this function. Okay, so I have the derivative of the top. So I have cos x times the bottom, cos 2x, minus the top times the derivative of the bottom. Well, the derivative of cos something is negative sine of that something times the derivative of the interior function, which is just 2. So notice this time I didn't put the 2 in front. I didn't kind of think ahead. So I just put everything in brackets to be really clear that this 2 does not get multiplied by the 2x. Now the denominator is cos squared 2x. Okay, now you can breathe a sigh of relief. You're done your derivative. I'm going to clean it up just a little bit. There's some negatives here that are kind of overwhelming me. So I have cos x times cos 2x. I have a negative negative, so I have plus 2 sine x sine 2x over cos squared 2x. Now you may be thinking, oh my god, this can be so hard for me to simplify. I'm going to have to use trig identities. But what's nice about questions like this is I don't need you to simplify this. All I need to know is the slope when x is equal to pi by 6. So all you're going to have to do is sub in x is equal to pi by 6. The slope then is going to be cos pi by 6 times cos 2 pi by 6, which is pi by 3, plus 2 sine pi by 6 times sine pi by 3 over cos pi by 3, and I'll just put the square outside, so it's going to make the math a little bit easier. Okay, that looks like a lot, but hopefully we can figure this out. If you're not, what's cos pi by 6? If you're not sure, you can draw that special triangle. It's the 1, 2, root 3 triangle. Pi by 6, well, this is pi by 3. It's the 60 degrees. Pi by 6 is actually the smaller angle. So cos pi by 6 is root 3 over 2. Cos pi by 3 is 1 over 2. Plus 2 times sine pi by 6, which is 1 over 2. And sine pi by 3 is root 3 over 2. And that is all over cos pi by 3, so that's 1 over 2 squared. Okay, how do I simplify this? Ooh. If I can squeeze all this in. I end up with a common denominator of 4. So I have root 3 plus 2 root 3 all over 4. Divided by a quarter, so times 4 over 1. So I end up with 3 root 3. Kind of skipped a few steps there, but we're running low on space. So that is my slope, 3 root 3. Now remember, I'm trying to find my tangent line, so now I have a slope. I need my y-intercept. A way to do that is I need to find another point. So I'm going to find another point at x is equal to pi by 6. That is, I'm going to sub x equals pi by 6 into y. So I get y is equal to sine pi by 6 over cos pi by 3. I can figure that out. Sine pi by 6 is half. Cos pi by 3 is also half, so that's 1. So therefore we have point pi by 6, 1. Now you have two options to find the tangent line. You can sub the point pi by 6 and 1 into the expression along with this slope, and you can solve for b. So to find equation of the tangent line, sub m equals 3 root 3 and point pi by 6 comma 1 into y equals mx plus b and solve for b, which is annoying because you have to do quite a bit of math. What's easier is to remember this formula. M is equal to the slope formula, y minus y1, x minus x1. If you cross multiply, you get m times x minus x1 is equal to y minus y1. Then you just sub in the values. So you get 3 root 3 x minus the x value, which is pi by 6, and y minus the y value, which is 1. So that's an easier way to find the equation of a tangent line, just by using the modified slope formula and just sub in the values, and you're done. This step you actually have to find a y-intercept, which is a little bit more math. And this is a perfectly acceptable answer. So hopefully you remember doing questions like that. The process hasn't changed, just it's a little bit more confusing because of trig. Let's turn la page. Okay, the two other types of questions that we've done related to calculus. It's a question like this. On the Indonesian coast, the depth of the water, the T hours after midnight, is given by this equation. So that tells me how deep the water is. What is the rate of change in the depth of water at 8 a.m.? So this kind of question we've seen, rate of change question. Rate of change is actually a nice question. It just means I need to find the derivative. So I need d prime. That's going to be, okay, well the derivative of a number is just a number. So this is going to be 6.8 times the derivative of cos, which is negative sine 0.507t. Okay, but I also have to multiply it by the derivative of the interior function, which is 0.507t. So just be very methodical in your work. Make sure, derivative is 0. Derivative of cos is negative sine. And so now I can just simplify this a little bit more. The derivative of 0.507 is, t is just 0.507. Multiply that by 6.8. And I get negative 3.4476 sine 0.507t. So that is now the rate of change of the depth of water. To find the rate of change when t is equal to 8 a.m., this is hours after midnight, so t is equal to 8. I just sub my values in. Just put that in brackets so it's clear what I'm doing. So I have 8 times 0.507, sine of that answer. Make sure, be really careful. That was a good kind of 0.507 times 8. That's a big number. If you were in degree mode, this would not work. Or no, sorry, make sure that you're in radians mode because there's no indication that this is degrees. Like there's no degree symbol. So I'm in radians mode, which is good. Press sine of that answer. And then I multiply by negative 3.4476. And I get 2.73119. So therefore, depth of water is increasing at a rate of 2.73. Remember, to figure out the rate of change units, you take the units of your y, which is meters, and you divide by the units of your x, which is hours, so meters per hour. Wow, the tide's really coming in at the coast at that time. 2.73 meters per hour. Cool, rate of change question. The final type of question that we would have looked at with calculus is an optimization question. A circular piece of aluminum of radius 10 centimeters has 3 segments removed. So I have a circular piece of aluminum, kind of a disc. I've cut out these segments to make this cool shape. And the angle of kind of this section that I keep is given in radians. There it is, theta. The remaining area after I cut off these 3 segments is this expression. Find the theta so that your area is a maximum. So in this question, I mean, I've kind of simplified it for you by giving you the expression. But technically, this would be enough without information without this to figure out this expression for area. That was, if you remember back to the optimization chapter, or section, that was one of the hardest things about optimization. We had to figure out this expression ourselves. In this question, I've given it to you though. I've given you the area. So now if I want you to maximize the area, I want you to find the max point of this graph, well, there's a process for that we learned. To find the max area, we need to find the derivative. So we're going to take, let's say, to find the max area. And we set it equal to 0. Hopefully you remember this strategy for finding the extreme points. So I have, let's call it dA d theta, so the derivative of a with respect to theta. I have this constant out here. You know what? Before I do this, let me just fix up a bit. A is equal to 50 theta plus 150 sine theta. That'll make things a little bit easier to understand. So now dA over d theta, the derivative is going to be 50 plus 150. Now what's the derivative of sine? Well, it's just cos. Okay, so now I'm going to set the derivative equal to 0. So I have 0 is equal to 50 plus 150 cos theta. I'm going to factor out the 50. And I'm left with 1 plus 3 cos theta. So for this to be true, 1 plus 3 cos theta is equal to 0. I have 3 cos theta is equal to negative 1, sorry. And I end up with cos theta is equal to negative 1 over 3. Oh boy, this looks familiar. I remember doing this when I had my special triangles. So we have to think. or sorry, trig equations. What angle has this ratio? I've seen 1 over 3. No, I haven't, right? Because I know 1, 2, root 3. So this one I don't actually know. I'm going to use my calculator to help me here. So shift cos 1 divided by 3. So that gives me a radian of 1.23. So if you can think about it, it's the related angle is equal to 1.23 rads. This is confusing, and this unit circle diagram is very helpful here. This is pi, so it's 3.14 units. So 1.23 units is somewhere here. But I need cos to be negative, C-A-S-T. So cos is negative, not in this, not within this quadrant, but in this quadrant. So if I have a related angle of 1.2, so that's somewhere up here. So there's 1.23. That's my first option. My second option is, I'll draw it in red, is down here. My related angle, same thing, 1.23. So the solution to this would be this one, which is pi minus 1.23. And I have another angle here, this red one, which is pi plus 1.23. I won't necessarily write that out. I'll just write out my two answers. Pi is equal to, or theta is equal to pi plus 1.23, and theta is equal to pi minus 1.23. Now, what was the question asking? Find theta such that the area is a maximum. Okay, so it has to be one of those two areas, or angles. Let me just double check and make sure this makes sense. So it's shift pi plus 1.23. That gives me 4.37, and I have shift pi minus 1.23, which gives me 1.912 or whatever. Okay, now let's just go back to the problem. Well, we know in this problem that the angle here, I mean, there's no restriction stated on it. I guess you could have the angle of this sector can be a lot bigger, so it could be up to an angle of 4.37. If you think about what that is in radians, so 180 degrees is 3.14 radians. So this is actually a huge area, like a huge sector like this. So I'm not sure that's what they're going for. If you can imagine that, like, I'll make a little note up here. What are the restrictions on theta? If you can imagine theta is equal to 0 rads, that would be kind of this angle would be 0. Kind of imagine it. And so you get this very, very tiny area. Right? You can imagine, like, because the rectangle's drawn from where the sector hits the circumference, and you get kind of this, it would be very, very small. If this angle was very small, you'd have this very, very narrow section. Meanwhile, the opposite would be, well, if the angle is huge. So if I draw the circle, right, and if your theta is humongous, and actually then you would end up with this very small, area as well, because you're drawing a line down, and so it'd be a very small area. Which happens for 3.14 rads. So then for this question, I would say that this answer is outside the bounds. And so my solution is pi minus 1.23. Now it also asked us to find the theta when area is a maximum and find the maximum area. So to find the actual maximum area, I'm going to have to sub this back into the expression. So I end up with A is equal to 50 times 1.912 plus 150 sine 1.912. And that gives me 236.93 centimeters squared. Kind of a confusing question. I mean, there's a few things here. The restrictions are confusing for sure, but this question follows kind of a very predictable pattern that we've done with optimization. Once you have a function in terms of one variable, you take the derivative, set it equal to 0, find the solution, and that's going to correspond to a max or min point. And there it is. So hopefully, I mean, that got scary really quickly, but the lesson itself, pretty straightforward. A lot of this then is review of calculus, which is not a bad thing, right? We can use all the review we can get. Your homework for this section is page 501, number 1 to 12, page 500, number 3 to 5, and 504, number 7 to 8. So there's a hodgepodge of things there. There's some optional homework, which is page 498, numbers 1 to 12, and 499, numbers 1 to 2. But I don't want to overwhelm you, and there's already lots there. So I've kind of tried to give you ones that are going to give you the best practice and best, not going to waste your time. But there are additional ones if you need the practice. Good luck with that, and we will see you next time.